Okay, so today we will continue to investigate the properties of the special theory of relativity. So we will discuss addition of velocities, relativistic energy and momentum, and then we will look at the covariant and contravariant transformations of the vectors and the tensors. So they are belonging to the Lorentz groups. So let us remember that the addition of velocities first. So suppose that we have one coordinate system, x1, x2, and x3, and another observer at another coordinate system, x1 prime, x2 prime, and x3 prime. So let's say that the frame is moving relative to the other one with constant velocity along x1, and the observer sees a point there, and the same observer sees the same point. So they have different space and time coordinates. So for this one we have what? CT and three-dimensional x, and for that one we have CT prime and three-dimensional x prime. So we can write that the Lorentz transformations in a differential format. So in the differential form, that is nothing but the following: dx0 is equal to gamma. So Lorentz factor between two frames, so gamma v is 1 over square root of 1 minus v square over c square or beta square. So Lorentz factor between the two frames, dx 0 prime, beta is v over c, so dx 0 prime c times dt prime, and dx 0 is c times dt. So we have dx1 prime, so x1 prime, yes, right? So this is the Lorentz transformation in one dimension, and one dimension is along the x1. So this is the transformation of the time coordinate. dx1 is gamma v dx1 prime beta dx0 prime, and perpendicular to the motion of the frames, nothing changes. That is equal to dx2 prime dx3 dx3 prime. So this is the standard Lorentz transformations in the differential form. So we can define that the speeds. So speeds seen in the prime frame, this is the prime frame, k prime, and this is the k. From the prime frame is dx I prime over c dx 0 prime over c. This is nothing but dt prime, because dx 0 prime is nothing but c times t prime, c times t prime, dt prime. So basically dx 0 prime over c is the dt prime. And another, the speed components of the speed seen from the k frame, let's say this frame without moving, that will be dxi over dx0 over c. I is 1, 2, 3. They are all spaced. Okay? No time coordinate, so I runs 1, 2, 3. So we can plug these informations to here. We can find the speeds very easily. So let us find the speed at this point parallel to the relative velocity and perpendicular to the relative velocity of the frames. That is very simple. So for parallel components, U parallel, so that is equal to the following. C times C goes up from here. So dxi is nothing but dx parallel. So what is a dx parallel? This is a dx parallel. This component is the Lorentz transformation parallel to the two frames. So that will be dx parallel over dx0. So this is the application of this very simple formula. So take the dx parallel and plug there. And if you do this, you will get the following. C times dx parallel is gamma v dx parallel prime beta dx 0 prime. That is this term, these two terms. So these are the parallel components in one dimension. Divided by dx0. dx0 is here. Again, everything is gamma parenthesis. Gamma v dx 0 prime beta dx prime parallel. Am I correct? So dx 0 prime plus beta dx prime parallel. So beta is v over c. V over c, magnitude of this relative velocity in one dimension. So one of the things we are seeing that gamma factors are canceling. So I will talk about this when we investigated the perpendicular component of the relative velocity seen relative to the perpendicular to the motion of the two frames. So I will discuss a little bit later. So take the dx0 parenthesis, and if you take the dx0 parenthesis, you will obtain the following. dx0 prime parenthesis, dx parallel prime over dx0 prime plus, these are primes, yes, beta dx0 prime. So take the dx0 prime parenthesis. So this will be cancelled and that will be that. Divided by, do the same thing here. 1 plus beta dx parallel prime over dx0 prime dx0 prime. So take the dx0 prime parenthesis. So this will be cancelled. So now you can see the definition of the speeds. So where is the definition of the speeds? So dx prime over dx0 prime should be what? That goes up, then goes the other side. U prime over c, and that u prime will be the u parallel prime, and this will be u parallel prime also. So parallel component of the speed relative to the motion of the frames seen at k frame will be the following. C times, instead of dx prime parallel over dx0 prime, you can write what? U parallel prime over c, and plus beta and divided by 1 plus beta, and instead of this you can write again u parallel prime over c. So let us organize these terms. So let me organize here. If you put the value of beta v over c, so what will happen? This is v over c, c's will be cancelled, and beta is v over c. That is equal to u parallel seen at the k frame, velocity seen at the k frame, parallel component to the motion of the frames will be u parallel prime plus v 1 plus v u parallel prime over c square. So if you write again this term, that is nothing but u parallel prime plus v 1 plus v dot u over c square. So they are the same thing. Projection of the u along the v is nothing but u parallel, and of course prime. That is prime. So this is the velocity addition for parallel components. Parallel components to the motion of the two frames. So what is interesting here, in Galilean transformation, you don't have this term. So basically, if you observe, suppose that in one dimension, if you observe the speed of light at k prime as c, with respect to the here, there should be what? If u prime, u double prime is c, so if you are observing the speed of light from the moving frame at c, according to Galilean transformation, the speed of light seen at the k frame should be c plus v. But in that case, if you say that, if you plug here c and c, what will happen? This will be c plus v. This will be v c over c square. That will be v over c. Take this to the other. V plus c's will be cancelled, and this will be the c. In both frames, you will see that the speed of light is a c. So in the extreme case, if you let u prime is c, then you will find that the u, what? C plus v 1 plus v c over c square. One of them will be cancelled. This will be c plus v, and this will be the c. So both frames will see the speed of light as c. So Lorentz transformation to the application of the addition of velocities tells us that in both frames we can see the speed of light as c. Now let us look at the perpendicular component of the velocity. So I take that the velocity along the direction of motion. So if you investigate that the perpendicular component of the velocity seen at k frame, what will happen? Or lab observer, whatever you call. K is the lab observer, K prime is the moving observer. If you do the same thing for the perpendicular component, you have to apply again the same rule here. C times dx perpendicular over dx0, and dx perpendicular doesn't affect it in Lorentz transformation, so that will be the same value, dx prime perpendicular, but the dx0 will be the time coordinate according to Lorentz transformation. That will be gamma v dx0 prime plus beta dx parallel prime. So that will be this term. So you can see automatically the one important difference. The perpendicular component to the velocities seen in the S K frame or K prime frame is proportional to the 1 over gamma. If gamma high is very high, that means that the perpendicular component of the velocity is almost 0. We see the similar structure if you remember that the light rays. Do you remember that last time I said that the tangent theta prime, so that was proportional to what? 1 over gamma and some stuff there. Okay, if the gamma high, theta prime for the light beam goes to 0, but for the velocities, the perpendicular components goes to 0 at high speeds. This is important for particular derivation of the relativistic momentum of energy. I will discuss, but I will give you the homework for you. I will do here as much more easy way in the classroom, but I will discuss how you are going to calculate. So if you do the same thing here, algebras, what you are going to obtain? So take the dx0 prime parenthesis, then you will obtain C over gamma v between the frames, dx perpendicular prime over dx0 prime. If you take this to the outside, and the leftover will be 1 plus beta dx prime parallel over dx0 prime. So I take the dx0 prime parenthesis and I obtain this term. I think this should be the perpendicular velocity, and this overall result should be the following. U perpendicular will be the C over gamma v, and that should be equal to x prime over x0 prime, U perpendicular prime over C, and divided by 1 plus V over C, and for this one you can write U parallel prime over C. So these C's will be cancelled, and you can write that for perpendicular component, that will be U perpendicular prime gamma V 1 plus V dot U prime over C square. This is the other term. And as I said again earlier, perpendicular component of the velocity seen at K frame, this frame, goes to 0 if the gamma factor is huge, if it is 1000, for example. That means that you will notice that only parallel component of the velocity. Okay, if these two frames moves with respect to each other v such that gamma is large, then you will notice the velocity here or there only parallel to the motion. The perpendicular to the motion goes to 0. That is important in the calculation of the collision problems. So that's all I want to talk about the addition of velocities. Now, another thing, you can easily derive that ratio. So I am not going to derive, but you can, as practice, you can do the following. You can take the ratio. So the ratio is something like this. U parallel, perpendicular over U parallel is tangent theta is U prime sine theta prime gamma V U prime cosine theta prime plus V. So you work on and derive this, but basically you are seeing that when gamma is high, the angle goes to 0. Just take the ratio. If you take the ratio, this will be cancelled, and you define that the U perpendicular over U parallel tangent theta and U perpendicular prime over U parallel prime is tangent theta prime, like we did 2 days ago for the beam of the photons. You can get the above result easily. Now, I want to define another thing related with the special theory of relativity. For velocity, using the for velocity, we can define that the energy momentum as a 4 vector. We can define also relativistic energy and momentum. So let us try to define for velocity. What we have at hand, we have the c, t, and x. This is a 4-dimensional space and time vector. If you want to define for velocity, what you have to do, you have to take the derivative with respect to time. But time is a little bit dangerous because time is different coordinates. We know one thing, everybody agrees, the proper time. So proper time is the same for everyone else. So basically what we do, we can take this is x0, we can take that the x0 and take the derivative with respect to the proper time. So this is the very important point in the spatial relativity. Proper time, or c times proper time, is the proper length, is same for every observer. So then dx0 over dt, d tau, let us call that the u0, 0 component of the for velocity. Simply by the chain rule, you can write this as dx0 over dt, dt over d tau. And you can automatically say that what is the dx0 over dt? C, because x0 is equal to ct. x0 is equal to ct, therefore dx0 over dt is c. And this is c. And what is the dt over d tau? What is the dt over d tau? From the time dilation we did. That is nothing but gamma. So look at your lecture notes. So dt over d tau is the gamma. So basically, zeroth component of the for velocity will be c times gamma. So here the proper time is playing very important role. This is the time coordinate. Take the derivative with respect to the proper time. Use the chain rule one information dx0 over dt is c, the other information dt over d tau is gamma. And also over the time dilation, moving clocks slower. And you can do the same trick to the space part more easily. So if you take the derivative of dx over d tau, and that will be what? Dx over dt, dt over d tau. Dx over dt is the ordinary velocity with respect to the time, and let us call u, and that is nothing but again gamma factor, and that is equal to gamma u. So basically the forward velocity is the following. So I am keeping this a little bit more. Let me erase the rest of the part. The forward velocity will be u0 and u, that is nothing but gamma c and gamma small u. So this is the forward velocity with respect to proper time. Now, using this, let us try to define that the relativistic momentum of energy. This is the simplest way. There are several ways of finding the relativistic energy and momentum. I will discuss, but let me show for the simplest one. Simplest one, what could be the simplest one? If you have a forward velocity, just multiply with the m mass. That is the simplest one. So what you can get if you multiply with mass, so you will get m times gamma c, m times gamma u. That is nothing but mass times u0, mass times u. And play the first term. Multiply by c by divide by c. What you are going to obtain? Take the gamma here, gamma m c square over c, and write this as a gamma m u. Actually, the first term is nothing but energy over c, zeroth component of the forward momentum. The rest is the relativistic momentum. This is the easiest way, but I will discuss about the other way of finding these results. So we can call this as a whole E over C and P. This is 4 vector, so this is the E over C, this whole stuff. This is the relativistic momentum, and that is equal to mass times, on the left hand side, mass times u0 u, this one. Now, so I find very easily the relativistic momentum and relativistic energy. There is one other way. You have, if you know that Lagrangian of the relativistic particle, even without interacting with the electric and magnetic field. If you know that the relativistic Lagrangian, you can calculate the canonical momentum, and that will be gamma mu or v. But defining the relativistic Lagrangian is a little bit tricky. That is not 1 over mv square type Lagrangian. We will discuss this next week. So once you know that the correct Lagrangian or set up the Lagrangian, you can calculate the canonical momentum. If you know that that will be gamma mv, and if you know that the canonical momentum, you can calculate. If you know that the Lagrangian, sorry, you can calculate the Hamiltonian, and Hamiltonian will be the gamma mc square or energy. So that is the other way of doing that. That is the way of the lambda Lifshitz, and I'll discuss this in the next week. But there's another way in your book. So last time, yesterday I studied and prepared lecture notes, but I'm not going to do. That will be part of your homework, okay? So because here 5 pages, it will take maybe 1 hour. So instead of doing this, I will let you as a homework, but I will discuss how you are going to do. The other approach is the following. 2 identical particles, mass m and mass m, is moving with velocity, with the same velocity. They will collide. So 2 approaches there. You can, okay, you will conserve the energy and momentum. It's a collision problem. But there's a 2 approach. If you look at from this to the collision, the coming object has a velocity not equal to 2v. That is equal to related this one, okay? Addition of velocities, one thing, one approximation. So if you go to the steps section of that related section in your book, you can see that, okay, one thing. So if non-relativist, if it were not non-relativistic, if you are an observer here, you will see that this particle is coming to you, coming to this observer by 2v. But here, you have to use that addition of velocities. The other thing, since they will highly relativistic, perpendicular component of the velocity after the collision will be almost 0. Okay, 2 things will be there, and if you go in this way, you will see that the mass is related with the velocity, and mass related to velocity, mass is related with the gamma times m. Okay, so that will be the homework. So I am not working on this part. It will take time, and that is a homework, and the section related that 11.5 relativistic momentum of energy of particle. So I don't know your book, Jackson, where get this derivation. I am following the one website developed the Stanford University. Susskind has giving the series of the lectures related undergraduate level. So there was a paper, 1905 paper of the Einstein for the first relativistic electrodynamics paper. I look at that. That derivation is not related to the derivation of your book. That is a little bit different. So if you are interested in, go to this page and find the Einstein's paper. That is related with the electrodynamics, motion of the charged particle in the electromagnetic fields, and he finds that the relativistic mass in that form. But the people in the common sense does not use a relativistic mass. So it is used in the undergraduate books, but in the physicists, they don't use a terminology of the relativistic mass, okay? They use that instead of, they use that relativistic energy or relativistic energy at rest. That means that the mc square. Okay. So this is a homework for you, and that homework is section 11.5. Chapter 11, section 5. So you will use this addition of velocities, and the perpendicular components of the velocities goes to 0 if the particle is highly relativistic. Now let us come to the easy structure here again. We have defined that the 4 vector there, and this is energy and momentum. What is the length of the energy of momentum? We call as a length, or the scalar product by itself. What is the length of this 4 vector? You know that. What is the definition of length? So we know this. If we have a dot a, it is a0 square minus a dot a. So what is the length of this vector? What is the length of this 4 vector? So tell me. So square of the first term, E0 square over C square minus P square. What is the right hand side? What is the right hand side? There is one M0 square, M square. And what is the U0U length? Length of the U0U. Let me do very easily. What is the U0U length? So that is equal to what? What is the U0U length? That is equal to, tell me, that is equal to U0 square minus U square. Or U square. So what is the U0 square? Gamma square C square. Gamma square C square minus minus what? Gamma square U square. Take the magnitude of this space part of the vector. So what you get? If you take the C square parenthesis, what you are going to obtain? So take the C square gamma square. Maybe you see already the definition. If you take the C square gamma square parenthesis, that will be 1 minus U square over what? C square. What is the 1 minus U square over C square? 1 minus U square over C square. U over C is the beta, B 1 over gamma square. That is 1 over gamma square. And this will be cancelled, and this is the C square. This is important. So length of the 4 velocity is all the time C square. That is invariant. So that is C square. And that is C square. So we find a nice formula. So you can represent this in the following form also. That is equal to E is equal to C square P square plus M square C to the 4. So take the P square other side, multiply by C square, and this is the, you know this formula. Now let us look at the following thing. What does it tell more, this equation? What happened for the photon? If for the photon, is there a mass? No. M is equal to 0. M is equal to 0. Then E is equal to CP. So if you remember that the last time when we derived at the relativistic Doppler shift, how we take the 4 wave numbers, V over C and K. What happened if I multiply by H bar? That will be H bar omega over C, H bar K. What is the length of this vector? What is the length of this vector? So what is the length of the above? Omega square minus C square minus K square is equal to what? We said last time that is equal to what? That is 0. Omega square C square minus K square is equal to 0 from dispersion relation. And if you look at from here, that will be 0. And what you are finding from here? So you will find from here what? From the length of this, you will find again what is the H bar K? What is H bar K? Do you remember? Momentum of the photon. Momentum of the photon. What is H nu? Energy of the photon. Did we find this? Yes. What is the length of this? 0. 0 here also. Okay. They are the same things. So last thing I can discuss, what happens at the low velocities. So this is the relativistic energy. Did you take the relativistic quantum mechanics yet? Okay, so if you take the square and the put instead of E and P is operators, that will be Klein-Gorgon equations, and that will be converted. So has some problems, and that will we will work on the Dirac equations eventually. Now, let us look at the moment. Let us look at what will happen at the low speeds. So this situation is the following. This is the energy. Take the C outside. P square, M square, C square. So generally, the momentum is less than mc at low speeds. And if you take the one more parenthesis of the mc out, you will get what? Take the mc out, that will be m c times c square, square root of 1, therefore that's 1. And the other one will be p square over m square c square. Okay, I take the mc outside. There's one c that makes mc square. This term is 1, that is p square over m square over c square. If p is less than mc, square is much less than mc, you can use that the binomial theorem. So if you make a binomial expansion, you will find mc square plus 1 over 2 p square over m square c square plus additional terms. So if you insert this, and this will be m square, mc square, the other term will be m c squares will be cancelled, p square over 2m. And there they have more other terms here. This will be the energy. So is this energy something we know? Yes, that is p square over 2m. There's the additional term here, but that is just a constant. So now I am ready to start a new part. So new part, so we summarize all properties of the spatial theory of relativity. Now we will investigate the Lorentz transformations and Lorentz groups, some properties of the mathematical properties. So let me start, and then I can give a break. So mathematical properties of the space and time. So basically, if you have a 4 vector, so x, this is the 4 vector, you can look at the magnitude we did, x0 square minus x1 square, x2 square, x3 square, and let's call that this is the s square, and we know that this is invariant. Invariant, doesn't change. We discussed this. So this is called a homogeneous Lorentz group. So this is the difference between what? With the 0. x0 minus 0 and x1 minus 0. If you look at the difference of the other location, you can define a s square xy, and that is nothing but x0 minus y0 square minus x1 minus y1 square and x2 minus y2 square, x3 minus y3 square. So here you are looking at the differences. This is not 0. So that is called as a inhomogeneous Lorentz or Poincare group. Lorentz or Poincare. So we are not touched to this inhomogeneous group, but we are investigate the mathematical form of the transformations. We work on the transformations, Lorentz transformations, by defining the Lorentz transformations or deriving the Lorentz transformations. So we know how to transform to vectors. So that is the first rank, and 0 rank is the scalar. That is same everywhere. So we have, in general, mathematical illustration is the following: x prime alpha. So from now on, as you will see that the index up or down will be very important. So alpha could be what? 0, 1, 2, and 3. And if we make a Lorentz transformation, we generally write this as a function of x0, x1, x2, and x3. Remember that we said that x prime 0 is the time coordinate. We write this in terms of this. We said that we can write this in 3-dimensional, then that will be the x2 and x3, other terms will be the important. So in general, the situation is the following. You have a prime frame, and you are trying to express the alpha is 0, that is time coordinate, alpha 1, that is the x, alpha 2, y, alpha 3, z, in terms of the unprimes. This is the mathematical notation. In general, you can write this to any kind of vector, like we see. What vectors we see? Energy, momentum. What else we see? 4-wave number. So in general, you can have many physically valid, not many, some physically valid 4 vectors. So, and the transformation property is defined in the following manner. This is important. So A is a 4-dimensional vector, and basically if it is a vector we call rank 1, rank 0 is scalar. If you make a transformation to the new frame, and in the new frame A prime alpha is 0, 1, 3, beta is 0, 1, 3. So mathematically we can express this in the following format. So del x prime over del x, and beta is sum, and alpha is a free index. So this is the mathematical presentation. This is important. So we are calling this as a contravariant vector. And we can transform this by using this notation. And beta is the, if you see that any index up and down, that means that a summation index. Okay, that means a summation index or repeated index implies a summation index. And this is the Einstein convention. He doesn't put a summation. Instead of use the one index up and down, that means a summation. The open form of this is the following. Okay, the open form is the following. Okay, I want to calculate that the A prime alpha. Alpha could be 0, 1, 3. It doesn't matter. So the open form of this is nothing but the following. Del x prime alpha over del x0 a0 del x prime of alpha del x1 a1 del x prime alpha over del x2 a2 del x prime alpha over del x3 a3. We will not write this all the times, but just to show you. Okay, if you see that the index up and down, that means that there's a summation. Sometimes it is called contraction. Okay, and if the index is up, it transforms as a up in this format. This vector is called as contravariant. I am forgetting sometimes. I will sometimes use the upstairs, okay, or up, okay. But the place is important. Contravariant means that the index is up. The opposite of this, as you guessed, if you think about that, this is a Lorentz transformation to prime in terms of unprimes. You can write the inverse of this. So inverse of this is called as a covariant. So in that case, the rule is the following. In the case of covariant, index is down, some beta, and you will make a transformation, and the final index will be in down. What do you think will be in between them? How you can define it mathematically? So we define that the del x prime over del x, to go to the a prime, you will define the opposite of this. As a pattern, you can get the following. So index is down, that should be sum up with the beta, and that goes to the alpha. Okay, so this is a covariant vector and transforms in the following format. And actually, if you look at the one-to-one, you can think about the boost matrix. So I think that was equal to cosine hyperbolic sine hyperbolic 0 0. Don't write this, and I think sine here, cosine here, 0 0 0 1 0 0 0 0 1. And if you look at here, so you can call that the elements of this boost matrix if you want. So this is the mathematical form. So alpha beta is related with the elements of the transformation matrix. We will come to this when we study that the transformation of the electric and magnetic fields. Now let me define that the rank 2. Rank 2. Rank 2 is tensor, yes. Rank 1 is vector, rank 0 is scalar, yes. So if you want to transform rank 2, let's say gamma delta, what kind of tensor? Contravariant. Variant. So that will go another f prime with new indices, let's say alpha and beta. What kind of transformation pattern I needed? I need to transform the gamma to the beta and delta to the beta, gamma to the alpha. So if I want to transform this, what I have to do, del x prime over del x, what? Gamma, delta go to the gamma. Beta. So these indices is sum up or contracted, and free index is beta. Okay? So tell me for the other one what I have to write. So just tell me. So I need to sum up this del x prime, say del x prime of alpha over del x gamma. So look at with the eyes. If you see a dummy, sum up those, they contract, and look at the free indices. So they should agree to each other. So I will show you the mixed one. Let us look at the mixed one. H gamma delta. So allow a space. It's up to you. Don't align up the indices. And H prime should be what? Some index alpha and here beta. So upper will be transformed as a contravariant, lower will be transformed as a covariant. So let us transform to the upper. So that will be what? Del x prime over del x of what? So this will be sum up and left a free index alpha. And the other is index is down, covariant, then there should be the opposite of it, del x over del x prime. And gamma in sum up, left a free index beta, if you have the mixed one. So did you get the situation? So let me tell you again, gamma and gamma is sum up or contracted, left a free index, and delta is sum up and left a free index beta. So maybe, yeah, that's okay. Now, these are the tools. We have a contravariant vector is transformed as a, let's say, Lorentz transformation in that mathematical pattern form, and covariant, let's say, inverse Lorentz transformation is transformed in that form. You can have the mixed one also. Now, after the break, I will define the scalar product. We said that the scalar product is not, it's an invariant quantity. Then we will define that the metric tensor will help us to lower the indices and get upward indices from covariant to contravariant and covariant to contravariant, vice versa. So why we are doing this? Our aim is to write the Maxwell's equations in a covariant form. That is different than this terminology. Covariant in that case is the same everywhere, every inertial frame. Okay, so we are trying to express the Maxwell's equations in a invariant as a form in different inertial frames, which is called covariant form.